All right, welcome back, you guys. Your favorite Calculus 2 course. So we're going to take a look at the last two, ratio and root tests in this sections. They're nice. They don't require us to find a comparable series. Um, and this ratio test will especially be useful in the discussion of power series in the next section. So hopefully you've seen that there's no single convergence test that works for all series. And thus we have a series of all these possible tests, right? We have a bunch of different tests. We're going to take a look at what's the use of this ratio test? Well, if you think about, was the limit of the nth term equal to zero? That's not a sufficient condition for the series to converge. It doesn't tell us for sure if it converges, right? We could not conclude that. We knew if it was not equal to zero that it diverged, right, by the nth term test. So not only do we need to know that it goes to zero, but we need to know how quickly it does that. So if you think about the harmonic series, we know this thing, 1 over n goes to zero, and also the p series 1 over n squared. Both of those go to zero, but by the p series, this one diverges, the 1 over n diverges, but by p series, the 1 over n squared actually converges, right? So this ratio test will provide us a way to measure how fast the terms of a series approach zero. So it can be useful for that. So that's just kind of the intro. So here's our ratio test, right? So what we're going to do is we're going to take the next term over the nth term, and we're going to see if it's less than 1, it converges absolutely. If it's greater than 1 or shoots to infinity, then it's going to diverge. And then it'll be inconclusive if that ratio is equal to 1. So that's our test. And just FYI, some textbooks will call that value rho. And then they'll just say if rho is less than 1, converges, greater than 1, diverges, and so on. Okay? So, although definitely not a cure for all ills, it is definitely useful for series that converge rapidly. So factorials and exponentials are very nice uses for this ratio test. So just keep that in mind. If you got a factorial or exponential, ratio test might be your way to go. Okay. As I work this first one, this solution, little commentary on this. Recall that the factorial function, thank you, grows faster than any exponential function. And so, and note also that the series has non-zero terms, which, by the way, that's a condition, is the series must have non-zero terms. So we're going to go ahead and apply the ratio test here. So we're going to take the limit a to the n plus 1 over a to the n, the absolute value of that. So that becomes, so I got 2 to the n plus 1 over n plus 1 factorial. There's my next term over the nth term, 2 to the n over n factorial. Okay? And so this becomes 2 to the n plus 1 over n plus 1 factorial. And I'm going to use the fact that 2 to the n plus 1 is the same as 2 to the n times 2 to the 1. N plus 1 factorial, if you think about your factorials like 5 factorials, 5 times 4 times 3 times 2 times 1, right? So n plus 1 factorial would be n plus 1 times n factorial, n or n minus 1 and n minus 2 and so on, right? So I'm going to write that n plus 1 factorial is n plus 1 and then n factorial down the line. And that's because I have an n factorial up there that I know it'll cancel with. So n factorial over n factorial, see that 2 to the n over 2 to the n So it looks like we're left with 2 over n plus 1. Well, as we run that to infinity, 2 over a huge number, right, we get 0. Well, it's 0, which means it's less than 1, right? I go back up here, look at it, and I'm like, oh, I'm less than 1. So this thing converges absolutely. The series that we were given, what was it, 2 to the n over n factorial, converges, and it actually converges absolutely. Let's go ahead and use the ratio test on this second example as well. So run the limit, n goes to infinity, a to the n plus 1 over a to the n. So we got n plus 1 being squared, 2 to the n plus 1 over 3. Oops, that's a 3 to the n plus 1. And this is all over the original nth term. So we got n plus 1 squared, 2 to the n plus 2, 3 to the n plus 1 times 3 to the n, and squared 2 to the n plus 1. N plus 1 squared. I'm going to write 2 to the n plus 2. I'm going to write that as 2 to the n, 2 squared. On the bottom, I got 3 to the n, 3 to the 1, n squared, 2 to the n, and 2 to the 1. Alright, let's start canceling some stuff. I got 3 to the n, 3 to the n, that's gone. I got, oops, that's a 2 to the n right there. Sorry about that. 2 to the n, and 2 squared. So I see my 2 to the n's are gone. I got 2 squared over 2. That leaves me with a 2 right there. So it looks like I got 2 n plus 1. Now if I divide everybody by n squared, right, everybody's by n squared, by n squared, by n squared, by n squared, then I've got 2 plus 4n over n squared, that'll be 0, plus 2 over n squared, that'll go to 0 over 3. So I'm just left with 2/3, which is again less than 1, so I know that it converges again. Therefore, by ratio test, a series converges absolutely. All right, we're going to go ahead and apply the ratio test on this next one as well. This will, notice I got the a sub n plus 1 term over the a sub n. Let's go ahead and clean that up. Multiply by the reciprocal here. So we got n plus 1 to the n plus 1 over n plus 1 factorial times we get n plus 1 to the n times an n plus 1 to the 1. This is over n plus 1 factorial. So I'm going to write that as n plus 1 and times an n factorial. And so it looks like we got n plus 1 and n plus 1. Looks like we got an n factorial and an n factorial. So we get n plus 1 to the n all over n plus 1 to the n all over n to the n, which is n plus 1 all over n to the n, which is that's the same as n over n plus 1 over n to the n. Which is 1 plus 1 over n to the n. And maybe at this point you remember the definition of E. Remember that was E? So this is E. Right? I'm running n to infinity there. This is E, which of course is bigger than 1, 2.718, right? Well, it's bigger than 1. Our ratio test then says that series diverges that we started with. So here we're going to show where the ratio test is not being helpful for us, but let's go ahead and run through it here. When we apply the ratio test, we'll have the limit n goes to infinity a to the n plus 1. So we got negative 1 to the n plus 1 square root n plus 1 over n plus 1 plus 1. This is all over negative 1 to the n, negative 1 to the 1, square root n plus 1 over n plus 2 times n plus 1, negative 1 to the n, square root of n. And I got square root n plus 1. I'm going to write this as absolute value negative 1 times absolute value. Then I got square root of n plus 1 over, I got a square root of n on the bottom, and then I got this n plus 1 over n plus 2. So absolute value of negative 1 is just 1. So I'm left with square root of n plus 1 all over n times n plus 1 over n plus 2. So I get the limit of this times the limit of this. I divide these all by n. And I got and over here I'm going to divide each of these by n. So I got square root of 1 times 1, which is 1, right? And so the ratio test, if it's equal to 1, the ratio test is inconclusive. So we need to apply a different test. Right? This ratio test is not helpful because we're equal to 1 here. And so note we can apply, this is an alternating series test. All right, we had, this was our, it was -1 to the n, square root of n over n plus 1. So here's the alternating part I circled. So the an part's right there. So number one, does it meet these conditions to converge? Well, we had to know that was equal to 0. Whoops, that has to be equal to 0, question mark. So limit n goes to infinity of the square root of n over n plus 1. Does that equal 0? Well, let's go ahead and divide by n, divide by n. Divide by n, well, that's the same as the square root of n squared, right? And so what we have is the square root of n over n squared, or 1 over n. And so this will go to 0, that'll go to 0. So I got 0 over 1 plus 0. So it does equal 0, so that's okay. First one's good. Second part of the alternating series test is the next term less than or equal to a sub n for all n, question mark, right? And so you've got square root of n plus 1, square root of n plus 1 over n plus 1 plus 1. Is that less than or equal to the square root of n over n plus 1? That's the question, right? Well, maybe it's easier for this one just to think about the first derivative test and just test it and see if it's decreasing or not. If you can't see it on that first one, so it's good practice. Let's go ahead and take a derivative of a quotient. Derivative of the top as the bottom minus the top, derivative of the bottom over bottom squared. And so this f prime of x will end up being x plus 1 over 2 root x minus root x all over x plus 1 squared. And so your f prime of x will be negative x plus 1 over 2 root x, x plus 1 squared. So your critical numbers for your first derivative test will be -1, 0, and 1. Now we don't care about down here because we're just looking from 1 on. So I'm just going to go ahead and test like x being 2. I throw that into my first derivative. So -2 plus 1, I get a negative on the top. The bottom is going to be a positive when I throw 2 in. So it is decreasing after 1. That's what we care about. So yeah, this is true. It's decreasing. The next term is always less than or equal to the prior term, right? So true from 1 on, right? So f prime of x less than 0 for x being greater than 1. Therefore, meets both conditions by the alternating series test. This series, sure enough, converges, right? It does converge. We could take this a little more. Furthermore, what about the absolute value? So, of the function. So that would just be the square root of n, this part, right? If I ignore the alternating, so it'd just be this part. The non-alternating part, the square root of n over n plus 1. Well, this will actually, this diverges if you can do it with the limit comparison test. With 1 over root n. So, therefore, this series is conditionally convergent. Just a note on this one. All right, we're going to go ahead and apply the ratio test I have written out here. So I got 2 to the n, 2 to the 1, plus 5 over 3 to the n, 3 to the 1 times. And so it looks like our 3 to the n's will cancel. Limit goes to infinity. 2 to the n times 2 plus 5, 3. You know what? Let me put that 1/3 out front times 2 to the n plus 5. And so I can split this up with that 1/3. I can split that up as separate absolute values. So I have limit and goes to infinity of 1/3. 2 to the n times 2 plus 5. 2 to the n plus 5. Divide everything by that 2 to the n. 1/3, 2 plus 0 over 1 plus 0. So I got 1/3 times 2, which is 2/3, which is less than 1. Therefore, by the ratio test, series does converge. And of course, yes, you could have used L'Hopital's, no problem. I just want to do it algebraically, so see that. Let me add a little bit to this note. This does not mean 2/3 is the sum of the series, right? In fact, this is the same as 2 to the n over 3 to the n plus 5 over 3 to the n, which is 2/3 to the n plus 5 times 1/3 to the n. These are both geometric series. And remember, the sum of a geometric series is a1 over 1 minus r, right? And so the sum of these, so the sum of this first one would be the first term, and we're going from, these are both from n being 0. All right, this was from 0 on. So 2/3 to the 0, the first term is 1 over 1 minus your r here is 2/3. Sum of this one over here would be 5 times 1/3 is 0, so 5 times 1 is 5 over 1 minus its r. And so you got 1 over 1/3 plus 5 over 2/3. And so you got 3 plus 15 halves, or 6 over 2 plus 5 over 2. So 21 over 2 is the actual sum of this series. All right, so don't get that mixed up with the 2/3. That 2/3 is just to test it, right? That's just for the ratio test. All right, so here I've applied the ratio test, a to the n plus 1 over 8n. First step, let's go ahead and multiply by the reciprocal here. So we got limit goes to infinity. Oh, I'm going to go ahead and distribute that 2n plus 2 factorial over n plus 1 factorial, n plus 1 factorial. And I might note for a minute, let me go aside here. 2n plus 2 factorial would be 2n plus 2, and then that's just reduced by 1. So 2n plus 1, and then 2n factorial keeps going down, right? 2n minus 1, and so on, right? Like, because 2n factorial would be 2n, and then it keeps going down by 1. 1 each time. All right. Like for example, if n is 5. If n is 5, for example, then you have 2n plus 2, that'd be 12 factorial. 12, 11, 10 factorial. If n was 5, then you'd have 2 times 5 factorial. You guys with me on that? So that 2n plus 2, I'm going to write that as 2n plus 2. (2n plus 1), and then I got that 2n factorial. And on this bottom, I'm going to write that as n plus 1, and then n factorial, and n plus 1, n factorial. And I'll see those cancel, n factorial, n factorial, n factorial, n factorial. So I've got 2n plus 2, I'm going to take a 2 out of that. 2n plus 1. I got an n plus 1. I got an n plus 1. So see how those n plus 1s cancel. So we've got 2 times 2n plus 1, or let me distribute that through 4n plus 2 over n plus 1. So I could use L'Hopital's or divide everybody by n here, and you'll end up with divide everybody by n. So you get 4 plus 0 over 1 plus 0. So we get 4, which is greater than 1. Well, if it's greater than 1 by the ratio test, the series diverges. Alright, started the ratio test on this. Multiply by the reciprocal there. So I got 4 to the n, I got a 4. I got n plus 1 factorial, so I'm going to write that as n plus 1, n factorial, n plus 1, n factorial. Here I've got 2n plus 2, so I'm going to write that as 2n plus 2, 2n plus 1, and then the 2n factorial. 4 to the n factorial, n factorial. Let's start canceling. N factorial, n factorial, n factorial, n factorial, 2n factorial, 4 to the n, 4 to the n, 4 to the n. I think I got everybody, so I got I got 4, n plus 1, n plus 1. I got 2n plus 2. Let me take a 2 out of that. And I got 2n plus 1. Notice my n plus 1s cancel. So we got limit n goes to infinity. I got 4 over 2. I got 2 n plus 1 over 2n plus 1. 2n plus 2 over 2n plus 1. I divide everybody by n. And I get 2 plus 0 over 2 plus 0. So I got 1. So, dang ratio test is inconclusive. Notice though that our an plus 1 over an, this ratio was 2n plus 2 over 2n plus 1, which is always greater than 1. Right? You see how that ratio 2n plus 2, regardless of what n is, the next term over its prior terms always greater than 1. So an plus 1 is always greater than its previous term, right? So this is increasing. Hence, all terms are going to be greater than the first term, right? And our first term, so an was 4n n factorial, n factorial, n factorial over 2n factorial. So the first term is 4 to the 1 factorial over 2 times 1 factorial. So we got 4 times 1 over 2 factorial, which is 2 times 1. And so this is 2. So a1 is 2. The first term is 2. So a1 is 2, and all terms are greater than 2 afterwards, right? Afterwards. Therefore, the limit goes to infinity. In other words, it's not 0. So by the nth term test, so by nth term test divergence, right, since one of the nth term is not equal to 0, the series diverges after all. All right, we're going to take a look at the root test now. So with the comparison test, the convergence test we have so far for an work best when the formula is relatively simple, right? So this next test, this is useful when we have nth powers. Okay, so this is when you want to use the nth root or the root test, right? And I just said it in two different ways here, but these are the same root test, right? So once you take the nth root of a to the n, if it's less than 1, it converges absolutely. If it's greater than 1 or shoots to infinity, then it diverges. And if the nth root of the absolute value of a to the n equals 1, it's inconclusive. Okay, so that's the root test. This bottom one is just another way. Some textbooks will call that value that you get rho. So just FYI on that, but that's the same thing, stating the same thing. So let's go ahead and apply the root test here. So we'll take the nth root, take the limit, then goes to infinity to the nth root of the absolute value of a to the n, a subscript n, the nth term. So limit n goes to infinity of the nth root of the absolute value of e to the 2n over n to the n. And so that's e squared to the n over n to the n. So that's e squared over n to the n. And so we've got the nth root of something to the nth power, right? So they'll undo each other. And so you just got e squared over n. And of course, you don't need the absolute values on these. E squared is positive. N is going to infinity. N is from 1 on, right? So that's positive. So we just got e squared over n. And n's going to infinity. So this will go to 0, right? E squared over a huge number. So we got 0. So all we care about is it less than 1, then it converges. So by the root test, since this thing is less than 1, this converges. And it actually converges absolutely. A more powerful statement there. So we get the nth root of that n squared. We drop that absolute value, and then we got the nth root of 2 to the n. And let me write this another way. That's the nth root of n squared. Nth root of 2 to the n is just 2. So I have n. Let me write this in exponential form. So that's n to the 1 over n squared. And I say that because as I run n to infinity, this will go to 0. So that's n to the 0. Anything to 0 is 1. So I got 1 squared over 2. So I got 1/2. Well, that's less than 1. Therefore, by the root test, this thing converges. Absolutely. These next two are really good U-triad problems if you want to pause it. Alright, so I've stretched out limit of the nth root the first couple steps here. So I'm to the point where I have the nth root of 2 to the n. So that just gives me a 2 on the top. And let me rewrite this as the nth root of n to the third. So you get the limit as n goes to infinity of 2 over n to the 1 over n to the third. And we know this part goes to 0 right there. And so we got the limit as n goes to infinity of 2 over n to the 0. That's a 1 to the third. All right. And so we've got this being equal to 2. Well, that's bigger than 1. So by the root test, since it's bigger than 1, the series diverges. So we've got the nth root of the absolute value of a to the n. So we've got an nth root of something to the nth power. So that's just going to cancel that. That's kind of nice. So you have absolute value of 1 over 1 plus n. Of course, absolute value, but this is all positive, so I can ignore the absolute value on this. Well, as this runs to infinity, I got 1 over 1 plus infinity. So this just ends up being 0, which is less than 1. Therefore, by the root test, this series converges absolutely. So this is kind of worth thinking about a little bit, you guys, and using the root test. You know, most of the convergence tests so far have been with relatively simple terms. You know, consider this a sub n, where you got for n being odd, it's this formula, but if n is even, it's a different formula. You know, you could write this out, but it's not geometric. The nth term test doesn't help, right? The integral test does not look promising. The ratio test produces this. So the root test is kind of the one that's going to help us out on this one. We're kind of stuck with trying it with the root test. And so we're going to go ahead and apply that root test. See if this will help us out. So we've got the limit, n goes to infinity, the nth root, the absolute value of a to n, which is, but we got two scenarios here. We have the nth root of n over 2 to the n, when n is odd, and we have the nth root of 1 over 2 to the n, when n is even. And so we've got that's n to the 1 over n, and the nth root of 2 to the n is just a 2. That's where n is odd. And then we got nth root of 1, which is just 1, over the nth root of 2 to the n. So this goes to 0. So I got n to the 0, which is 1. Nth root of 2 to the n is 2. So that just ends up being a half when n is odd. Nth root of 1 is 1. Nth root of 2 to the n is 2. Oh my gosh, look at that. So I get a half for both of these. And so a half is less than or equal to the nth root of a to the n, regardless of the formula, less than or equal to 1/2. And by the squeeze theorem, the sandwich theorem, whatever you want to call it, the limit n goes to infinity of the nth root of the absolute value of a to the n is 1/2. Well, that's less than 1. Therefore, this series converges absolutely by the root test. So a little bit of strategies for tests, so kind of a summary for this sequences and series. You know, we've got 10 tests of infinite series, right? It really comes with practice, but here's some nice guidelines. This is kind of my favorite one. You know, can you use the nth term test if not, and you know, if the limit as n goes to infinity, the nth term is not equal to 0, well, gosh, you know it diverges right off the bat, right? Secondly, is it a geometric, or is it a p-series, or a telescoping, or is it an alternating? Well, if it's one of those 4, I'm going to use one of those 4 tests, right? The third one, well, maybe if it's not those situations, now let's think about integral, root, or ratio, and so on. And that's kind of the process that I'm going through usually. You can read a little bit more here if you want to. This is just another alternate thought process as far as application. But you know, the objective is I'm just trying not to waste time, right? I'm just trying to get to the one that works as quickly as possible, so I don't have to run through them all. So let's apply a few strategies here for this first one, right? So I'm looking at this and I'm like, gosh, you know what? The limit of the nth term, if I divide everybody by n, would be 1/3. Well, that's not 0. So I can conclude right away by the nth term test of divergence, the series diverges. You might notice on this one, you know, you could use the root test. You could also use the fact that this is a geometric series with r being pi 6. Well, if r is less than 1, you know the series converges. And in fact, you could actually find the sum too, right? A sub 1 over 1 minus r. Well, this one you might look at it, and maybe you're thinking, well, this is positive continuous decreasing. It's really easily integrated. Positive continuous and decreasing. So I can use the integral test, probably be most appropriate for this. So we're going to go from 1 to infinity of x e to the negative x squared dx, where I'm going to let u be that negative x squared. So I just need a negative 2x. I got to offset that. And then I'm going to run that limit. This is an improper integral, so b's got to go to infinity of negative 1/2, 1 to b of e to the u du. All right. And so yeah, we can integrate this thing, and of course it meets the conditions for that test. So we got limit b goes to infinity at negative 1/2. I got 1 over ln of e. I'm integrating e to the u. So 1 over ln of e to the u. Well, u is that negative x squared. And I'm going from 1 to b. Of course, ln of e is just 1. So I got limit as b goes to infinity of negative 1 over 2e to the x squared from 1 to b. Plus 1 over 2e. If you notice as b goes to infinity, this will be 1 over 2e to this huge number. So this will go to 0. So I just got 0 plus 1 over 2e. So I got 1 over 2e. And so the integral converges to 1 over 2e. That means the series will also converge. I'm going to look at this. How about with a comparison test? Let's use the limit comparison test with Bn being 1 over n. That's that harmonic series, right? Where 1 over n to the p. So our p is 1 here. So by the p series test, we know this. We have p equals 1. 1 over n to the 1 power. P is 1. Well, if it's less than or equal to 1, greater than 0, this was the one that eventually, very slowly, diverges. But it diverges by the p series. So if we use the limit comparison now with that, so we run the limit, n goes to infinity of the original over that comparison one. We'll have the limit, n goes to infinity of 1 over 3n plus 1 all over 1 over n. So we'll have the limit, n goes to infinity of and then we divide everybody by n, and we get 1/3. Well, if it's positive and Bn diverges, then we know by the limit comparison test that An will also diverge, sorry. Now hopefully you see this is alternating on that. So we're going to run the alternating series test. So limit, first of all, limit as n goes to infinity of An, is that equals 0, question mark? Let's see. 3 over 4n plus 1. Yeah, that goes to 0. So this equals 0, check mark, that's true. Does a sub n plus 1, is that less than or equal to a sub n for all n? Question mark. 3 over 4n plus 1 plus 1. Is that less than or equal to 3 over 4n plus 1? 3 over 4n plus 4 plus 1, so 4n plus 5. Is that less than or equal to 3 over 4n plus 1? Yes, it is. That would also be true. So it meets the conditions. So yeah, the series does converge by the alternating series test. Well, in this one, I'm noticing this nth term, we have a factorial here indicating ratio test may work well. May work well for us. So let's go ahead and run this ratio test. So I got n plus 1 and factorial 10 to the n, 10 to the 1, 10 to the n factorial, n factorial, n factorial, 10 to the n, 10 to the n, n plus 1 all over 10. Well, as we run this to infinity, see our numerator just keeps getting bigger, bigger, bigger. So this runs to infinity, so the series diverges by the root test. On this next one, if you notice here, notice that we're raised to an nth power, indicating that root test might be very favorable. So let's go ahead and run the root test on this one. The nth root of the absolute value of a to the n. Nth root of something to the n, so we've got limit as n goes to infinity of n plus 1 over 2n plus 1, and notice those are all positive. So divide everybody by n, we just end up with 1 plus 0 over 2 plus 0, so we got 1/2. Well, that's less than 1, so we can conclude by the root test this series converges. In fact, it tells us that it actually converges absolutely. Well, I hope that kind of helped with a few strategies as well with these series. And thanks for watching, taking notes. See you next time.